Hello, everyone. How's everyone doing? Awesome. All right. This talk is Beyond Two Groups, General Bayesian Testing by Eric Ma. He has an open space later today that he'll be telling you about, and that is where you can go and ask questions. So please hold your questions for the open space later. And Eric Ma.
Hello, everybody. How are you all doing? And how has PyCon been? Pretty awesome? Yeah, cool. I've been on staff for a few years myself. PyCon's one of the highlights of my year, and it's really amazing that we were able to get so many people here. I'd also like to thank you all for coming to my talk today. The title, you can see it on the screen, Beyond Two Groups, Generalized Bayesian A, B, C, D, E, F, G testing. At the end of it, I hope it's pretty clear to you that this is basically my rant against canned statistical procedures, all right? We do not want canned statistical procedures. We want to do our statistics in a more principled fashion, and Python can be a great part of that. A little bit about myself, just so that you have a flavor of who I am. Currently, I work for the Novartis Institutes for Biomedical Research. We do data science. I'm on a team called Scientific Data Analysis. My official title is investigator, which sort of means I'm allowed to do researchy things. Scientific data analysis is basically one of the most generic names you can think of for a team that's embedded in a company whose bread and butter is science, all right? Prior to that, I was an Insight Data Science Fellow, and prior to that, I did my thesis in the Department of Biological Engineering at MIT. It was a journey for me to go in through the back door and out the front door, and then if people want to hear it, you can open space is open for that, all right? Finally, a little bit about me and Python, right? Python for me has been a very productive language because it's been the language in which I've been able to learn a lot of math. Things from Bayesian stats to machine learning to network science. Without the programming language as a tool to aid in my learning, it would have been much harder because this interactive nature of programming really aids in the learning. And beyond that, a little note about Python. It's one of those things where I've heard people say that Python is just like the second best language for everything. And like, the key word is not second best. The key word is everything, right? There's rarely one language that lets you go from the web to data science, to munging data, to DevOps, to SysOps, et cetera, all while sticking within one language. So it's great, and I hope you all have the same sentiments. Okay, so why did I make this talk? I made this talk because I saw a gap in the data science so-called talk literature, in which most talks tell you how to do an A/B test, Bayesian style or frequentist style, and they show you two groups, and they tell you about the t-test. And then they tell you how to apply this to your business case, et cetera. So in response to that, I basically have three messages. The first message is, you don't have to be stuck with two groups. And more importantly, you don't have to be stuck with the assumptions of the t-test, which are basically normal distribution assumptions. The second message I have for you is related to the language. Python, and more specifically PyMC3, is a really great language for probabilistic modeling and for doing your stats in a principled fashion. And that's the third point, that with Bayesian modeling, we can move away from these canned statistical procedures that have been handed to us in our university classes and our university stats education, and finally start doing stats in a more principled fashion, all right? Okay, so this is a talk this is a statistics talk disguised with Python. And so I am assuming a few pieces of knowledge here, all right? And I'm putting this out here for the benefit of you, the audience, so you can make an informed decision as to whether you would like to continue in this room or if you'd like to move to a different room. And I don't mean this in a way to exclude people. I just want you to have an informed decision, okay? So first off, I talk a lot about probability distributions, and I name them in passing in this talk. So I am assuming that when I name a probability distribution, you're able to conjure up in your mind what its shape roughly looks like, what it's used to be modeling, what it's used for in modeling work, and what values for which this probability distribution are valid, right? Probability distributions, by the way, as a working definition for today's talk, we're just going to call it credibility points assigned on the number line. And so when I talk about strong belief or weak belief inside, strong or weak belief for the value of a particular parameter, a strong belief, all I'm saying is that I'm willing to assign a small range of numbers credibility points. So we have a narrow distribution. And a weak belief says I'm willing to assign a large range of numbers credibility points, and therefore we have a wide distribution. Okay? So the distinction between continuous and discrete is also important because the two examples that I will show involve one continuous and one discrete data. Now, because this is a talk on Bayes, we have the obligatory Bayes rule slide. And so what is Bayes rule? Bayes rule is a neon sign that lives on the Bayes rule is a mathematical routine. For working definition for today, Bayes rule is a mathematical routine that lets us update our beliefs about a particular parameter having seen new data. All right? That's all it is. We don't need to worry about what the mathematical routine is, thankfully, because PyMC3, which is the package in which I have implemented all of these models, PyMC3 does all of the fancy math for lazy programmers like me, right? So PyMC3 is a great language, a great package written in the Python language for doing that. And I will assume some familiarity with PyMC3 syntax. Now, this isn't to say that if you don't understand PyMC3 syntax, you shouldn't be here. It just means I will go a little bit slower during the code portion for the benefit of those who need it. That said, if you've never touched PyMC3 before, my hope is that by looking at the PyMC3 code, you'll intuit how we've told the data generative story of our models in such a plain language way that we can just intuit it from the code, all right? All right, so comparison. Comparison is the basis of how we do science. And this video here shows the late Hans Rosling, a statistician who's great at storytelling. And in one of his books, he wrote this quote: "When I see a lonely number in a news report, it always triggers an alarm. What should this lonely number be compared to?" Implicitly, what he's saying is, what is the baseline? And what is the baseline that we're comparing our intervention against is basically what we're doing whenever we're doing science. And when we do the statistical analysis of that data, typically we're thrown two groups. And it's my hope to tell you, we don't have to stick with two, okay? So I'm going to tell you two analyses that are lifelike. I'm clearly not showing real data here because of confidentiality issues or because they're borrowed from a different source. But I'm going to show you two analyses that are lifelike and will simulate for you what they look like. The first vignette will tell you how we do an analysis that moves beyond two groups. And the second vignette will tell you how we move beyond t-distributed data in addition to that. So let's look at vignette 1. This story comes from a paper written by John Krushke in 2013. And it's a paper that talks about the intervention where we give participants in a trial a drug, and then we measure their IQ post-intervention. So we get data that looks something like this. Just a quick poll. How many of you have seen a chart that looks like this? This is a cumulative distribution plot. Great. So I don't really need to explain too much about what it says. Just very quickly for the benefit of those who haven't seen it, the x-axis, we have the values that we've measured. On the y-axis, we plot what cumulative fraction of samples have that value or less. And so the tails of the distribution are on the left and the right. The meaty part is in the middle. And we have two groups shown over here. We have the placebo group, which is our control group. And then we have the drug-treated group, which is our intervention group. Marketers call this A/B testing. I don't know why we have to invent yet a new term for case control testing, but yes, that's the alternative term that people will use. Okay? So when you look at this, you think, well, yeah, okay. What statistical procedure could I use here, right? So we go back into our university textbooks, flip back our notes from college, find Stats 201, and they tell us, use the t-test. So we run a t-test, And how many of you see that p-value, that juicy, juicy p-value of 0.025? Things are statistically significant. It's awesome. We can publish this paper, right? This drug can go to the trials, right? No. As it turns out, we missed out that there were 2 other groups. And if we were a dishonest scientist, we'd stop there. But we couldn't mask the fact that we've got 4 groups here. So now what's the canned statistical procedure for 4 groups? So we go back to our textbooks, go back to our notes. Stats 201 didn't teach that, so we go to Stats 211. Stats 211 says there's this thing called an ANOVA, and you might be able to do a Posthoc Ttest. So we whip out SciPy, and then we do the ANOVA, and oh no! That p-value is 0.09. This thing is not statistically significant. What are we going to do? The whole thing is gone crumbling down in front of my eyes. Well, it's okay. Even if this thing is not statistically significant, that's fine. Let's just do the post-hoc t-tests anyways, right? And so how many post-hoc t-tests do we have to do? Well, we have 4 groups. We do pairwise t-tests. And so we have 4 choose 2 number of tests, right? And so we put this in, and since we have more than one test, one hypothesis testing going, we do the French Revolution thing. We bring out the guillotine, and we start chopping out hypotheses that are not significant, and we tremble before the guillotine, asking when will we get a significant hypothesis test? Oh my, what an emotional roller coaster. Is this the right way to do stats? Is this the right way to do science? Do we really have to bring out the French Revolution guillotine in front every time we have multiple groups? Moreover, think about the case where we don't have just 4 groups tested. We have 50 groups tested. Suddenly we have more than 1,000 pairwise tests. And that guillotine is going to have a field day, chopping out hypotheses, pairwise hypotheses tests that are not significant. There's got to be a better way. And you know, when I see a scientific article that says like, or someone says that science has proven this and proven that, first question I ask is, what have they disproven? Second question is, how did they do the stats? Was it a p-value that they calculated? I don't quite believe that just yet, all right? So there's got to be a better way. In particular, let's think carefully about the assumptions that we make every time we do the t-test. Every time we do the t-test, we are assuming a bunch of things, these 3 being the key. Firstly, that our data are normally distributed. IQ, you probably could make a case. But what if you had other things? Not necessarily true. Why would we throw the canned statistical procedure at non-normally distributed data when we're assuming normally distributed data? Secondly, we assume that the standard deviations between the groups are equal. What if that's not true? What if we need a way to flexibly model that? Thirdly, what if our samples were not independent? Now, in a randomized controlled trial, hopefully someone checked. Otherwise, our drug trials by our company would be done wrong, right? Hopefully someone checked. But what if that assumption doesn't hold true? We can't do the t-test. So what canned statistical procedure is there? So I propose we stop assuming things and stop implicitly violating these assumptions. And instead, we do it Bayesian style instead. All right? So let's carefully model the key components of this problem. What are the key components of this problem? Well, we got data. We need to know what its likelihood is under a particular model. And then we need to find out and compute what the key parameters of this model are and what their most likely parameters are. And then for each group, do the same thing and compare those key parameters. That's all we need to do. So we go in, we write some PyMC3 code. PyMC3 code is written like this. You'll notice, first off, there are these things called pm.normal, pm.half-Cauchy, pm.exponential, and there are all of these great first-class citizens called probability distributions. So we can assign them to variables and we can do math with them. So for example, I'll model our data maybe as a starting point with a student t-distribution, because there's a case that multiple factors affect your IQ, and so as a result, the resultant IQ may potentially, in a hand-wavy way, be t-distributed. The student t distribution has a few key parameters. It's got a mu, it's got a standard deviation, and it's got a degree of freedom parameter. Remember that point that I made about having non-equal, not necessarily equal standard deviations per group? Well, as it turns out, we can model standard deviations on a per group basis using PyMC3. All we have to do is specify that it's a vector of standard deviations, one per group, and then pass that into the student t distribution, right? So those are the key things. We can explicitly encode what we are assuming about our data inside the probability model. In other words, lay out all the cards on the table. And if you're not happy with those assumptions, bring me a different distribution and a justification for that. How do we analyze the results of a Bayesian model? Well, first off, there's no k-choose-2 pairwise hypotheses test that we need to do. All we have to look at are posterior distributions. This is one particular representation of how we look at posterior distributions. This is essentially what we call a forest plot. And in a forest plot per group, right? Each of the groups are the horizontal, are the rows here. Per group, we can plot out what the median of the posterior distribution is, what the interquartile range is, and what what a percentage credible interval would be as well. And those are the dots, the thick bars, and the thin lines, respectively. All right? And all you have to do is look at that and say, yes, studying turned out to be the better intervention. And actually, I don't even know what this drug is doing. Is it making you stoned or something? Because, like, compared to drug plus studying compared to studying, you actually have lower IQ, right? So I don't know if this is like the thing that was most recently legalized in Massachusetts. So all we have to do is compare posteriors and compare this, by the way. Look at this versus that. Would you rather kneel beneath the guillotine waiting for a hypothesis to be proven true, or would you rather just look at the posterior distributions? And moreover, what's really neat here is the posterior distributions tell you the credibility assigned to the particular values. Plain and simple, nothing fancy. So, two key lessons from this particular analysis. Firstly, all you need are posterior distributions. You didn't have to do the multiple hypothesis correction procedure. Could we still be wrong? Yeah, of course, because our data are assumed to be generated by a random process, and so if we, by chance, had the wrong sample, a non-representative sample, well, we wouldn't have the correct inference. But it's harder to be wrong when you go with Bayesian procedures. Secondly, there should be nothing that stops you with two groups. PyMC3 code basically lets you write these things called a vector of probability distributions, in which you can use each slot in the vector to model one group, and do all of your inference in a nice principled fashion, all right? Cool. So I sort of gave you a semi-cheating example in which IQ, there's sort of a case to be made that it's maybe normally distributed, but what if our data were not t-distributed? T-distributions and normal distributions are in the same family. Well, that's when we come to the second vignette. And this is one where we're talking about clicking on websites, right? And this is an example that came to me last year after I did my tutorial with my co-instructor, Hugo. And I was holding office hours in the Tejas room in the AT&T Center in Texas. And this guy comes up to me and asks, hey, I got some data. Turned out to be his company data. I got some data, and I need some help looking at it. Would you have some time? And I said, like, yeah, sure, I got half an hour. We can totally sit down and look at it. 3 hours later, we were satisfied. And the process was very illuminating. So let's take a look at what that data looks like. The data looks something like this. This is a company that has a website. They're helping with booking of hotels. I won't say which company it is. There's basically things that they did to the website to try to improve customer engagement and clicking and revenue, all right? So they have the control, which is don't change anything as is. Then they have a first intervention, which is let's sort all of our results by price by default, okay? By default, we sort them by price. And the second intervention was completely independent. Let's just put images of the hotel rooms on the search results, like little thumbnails that you can see. And how do we measure customer engagement? Well, there's a way to do it. We will measure how many times they click before they stop clicking. right? And so basically, we want to know which intervention helped our customers find what they're looking for, and that's how we measured it, all right? So what are you going to do with that data? You're going to do the t-test? Are you really going to do the t-test? Like, does the t-test stand here? Or firstly, I don't think so. Firstly, we have zero inflation in the data. Look at the data. There's this big bar on a log scale that says that there's a bunch of stuff with 0 clicks. So the t-distribution completely does not hold. If you did the t-test, you are wrong, okay? Because the t-distribution assumes that you can take values from -infinity to +infinity, and that you're continuous. What are these data? 0 to +infinity and discrete. So again, if you did the t-test, you're wrong. We need a model that allows us to account for this thing that we call zero inflation, and we need a discrete distribution model for this data. All right, so 3 hours of modeling later, we arrive at the conclusion that the zero inflated negative binomial distribution, that long mouthful name, is actually the right thing to describe this, to describe the data. And why is that the case? It's because the zero inflated, the ZIN-B model, the ZIN-B distribution, is a distribution that lets us model 2 processes. The first process is the group of customers that have no intent to click whatsoever. They're just looking around. The second process is the process that describes the customers who are looking around. Sometimes they see the result and they make the purchase straight away, so 0 clicks. And sometimes they need a first and a second and a third and a fourth clicking around before they actually make that purchase, all right? So the zero inflated negative binomial distribution turns out to be the distribution that models this process. Now, our friend here was like not convinced. He said, we really got to try the t-distribution, and I let him try it. It didn't turn out well. But he needed to see it in order for him to be convinced that this was true. So in PyMC3 code, it turns out, look, we have the zero inflated negative binomial distribution. A lot of probability distributions are first-class citizens there, and this particular so-called mixture distribution is also one of them. And in fact, you can make a mixture distribution of your own. Moreover, here's what's really cool. Because of the data generating process, there are 2 very interpretable parameters that we're interested in. Firstly, we're interested in knowing whether the intervention changes the probability of a customer just searching around to actually being intended to click, right? Click around and make a purchase. And the second thing that we're interested in is whether the clicking process is affected, or the probability of making a purchase is affected each time the customer clicks, all right? So that's what, and those are calculatable, and I'd invite you to take a look at the code. I won't dwell too much on it, but that's modelable if you know just a little bit about the math behind the equation, all right? The negative binomial distribution. So what did we find? We found that putting images of rooms actually increases the probability of your customers clicking on anything at all, right? So they're moving away from this, this mode where they're just looking around into this mode. We're capturing more customers that are actually actively seeking to purchase things. And that if you put an image of the room on, compared to sorting by price, you actually you maintain the probability of purchasing an item. So it actually reveals something interesting about the customer behavior. These are not your price-sensitive people. These are your value-sensitive people, the people who want value for money more than the best price, right? And so we would not have been able to do this if we just stuck with the t-test and blindly assumed all of the things that the t-test assumed. Instead, because we sat down and we did the hard thing, but the right thing, and carefully modeled the data generating process and did our checks to make sure that it was modeling it correctly, we're able to arrive at this new insight onto his data. And this insight on his data was illuminating for the business and valuable. And you can actually tag a loss function on top of that and calculate how much this is tied to dollar amounts and make that interpretable for executives. You couldn't do that with a p-value, could you, right? Okay, so the key takeaways. Firstly, from this example, 3 or more groups are possible. Totally possible. There's no reason, again, to limit yourself to 2 groups. Secondly, all we're doing is comparisons. And who said that t-tests were the only way to do comparisons? As long as you're comparing a consistent quantity, that works fine. Finally, this was a neat insight for me. Sitting down, carefully constructing the Whitebox model, it lets us tease apart the interpretable things that are important to the business. And me coming in as like an outsider and not even knowing any of this for me was an epiphany. Now, this might be a bit more obvious to the guy who I was working with, but for me, wow, this is powerful. This is really powerful stuff. All right, so back to my 3 messages. I hope it's clear. From this talk, you can totally do your analysis without needing to be stuck with 2 groups and normal distribution assumptions. Secondly, PyMC3 is a great flexible language for probabilistic modeling. There's a wealth of talks that are out there, and tutorials even, on how do you use PyMC3 to do your probabilistic modeling. I encourage you to check those out. And finally, when we go Bayes, we can move away from canned statistical procedures and instead now do statistics in a principled fashion. And the bonus message here is you can better interpret your data with Bayesian methods. Thank you. Yeah, you can do.
We have time for a couple of questions. If you have a question, please walk up to the mic because all the Q&A is being recorded as well. So
and please
walk
phrase
up.
your question as a question.
Yes. Thank you. 2 questions only.
Thank you for the talk. I know it's not a question.
Okay,
My
all right,
question,
I'll dig
though-
that. We can talk more, actually, as well.
My question is, a lot of this seems based on picking the right distribution to match your data. How do you do that?
Gotcha. So the question is, for the benefit of others, how do you pick the right distributions for your data? I'm going to point you to 2 resources. The first is the PyMC3 docs, because they tell you, so the first way of picking distributions is to make sure that you pick a distribution that has the correct support, that is, the values for which it is valid. So if you got something that can never take on negative values, if you got data that can never take on negative values, don't pick a distribution for which the distribution actually can take on values, negative values. The second way to do this is to know the probability distribution stories. And so there's this instructor at Caltech who I've met at the SciPy conferences. His name is Justin Boyce, B-O-I-S. And he wrote this really great resource online about probability distributions and their stories. So he tells us what the story is for the binomial distribution, the negative binomial distribution, the exponential distribution, the normal distribution, et cetera, et cetera, et cetera. And once you know the distribution stories, it becomes really easy to pick out the appropriate distribution for the problem at hand. Now, finally, there is some model checking that's involved, and I've glossed over that over here. You got to do that model checking to make sure that the model is correct. And sometimes it's not a single distribution, it's a mixture distribution. And we got to do the right checks to make sure that's correct. Next question.
Quick disclaimer, I'm not trying to start a frequentist Bayesian war, but my question is, if you're doing multiple hypotheses at once, isn't some sort of correction still needed? Because just by chance you'd expect that one of your 100 or 200 or whatever different categories just happens to be an outlier in what sample you assign to it, and so it will appear to perform better than the control, and you might spend a lot of work trying to implement that when really it is the same.
Right. It speaks to the point that I had made earlier on that we might be wrong about our inferences because the data, as you mentioned, just came by random chance from a non-random sample, non-representative sample. So I actually had that question when I first made my first notebook with 3 comparisons. And I went online and asked Alan Downey, professor of computer science and statistics and data science at the Olin College of Engineering. And I asked him, do we need multiple hypothesis correction? And his answer was no, because, and he didn't give me the rigorous answer, and I'm unfortunately not able to give you the rigorous answer either, because I don't have the requisite training. I'm a statistician midway through grad school. But the answer there, the reasoning there was because we've summarized everything that we need to know, having seen the data, in the posterior distribution. And so the posterior distribution tells us everything, and there's no hypotheses that we've constructed that we're explicitly testing. All we're doing is looking and comparing what the data tell us, conditioned on our priors, conditioned on the data. And I'm happy to talk about it more during the open space. So there will be I have Bayesian open space, or Bayesian office hours as an open space later in the day, and I'm happy to talk with more of you if you'd like to talk about it. And please don't bring your data to me. Thank you.